All right, we're back and we're on page 302, and we're going to talk about more ways of finding derivatives. So far, what we have is we know a couple of rules. So let's go through and highlight them in weird ways. So we know the constant multiple rule, right? That just says the derivative of a constant times a function is the constant times the derivative of the function. Not a big deal. I mean, it's a big deal and you use it all the time, but it's like not it's the most straightforward of all the rules. Everybody uses it. Nobody even thinks about it. The next set of rules, also, no one ever thinks about it. We got the sum and difference rule, right? Which says that the derivative of a sum or difference is the sum or difference of the derivatives. Also very straightforward. Use it all the time. You never really think about it. The next rule is the power rule. We use that and we think about it because you do have to like put a little mental effort into it, especially with rational exponents. If you see a radical, instantly change into a rational exponent, use power rule. So we have this. Those are the ones that we know so far. So what we're going to talk about now is the product rule. What we'll talk about next is the quotient rule. Eventually, you will talk about the chain rule. You don't need it for a while. You need to get really, really good at using the rules that you do know. So don't even worry about it. Next year, you will learn it in detail very quickly. So don't even think about it. Just focus on what I'm going to show you now. So here we go. The product rule. So the product rule is a method of taking the derivative of a product. So a product is two things being multiplied. We can use the product rule on that. Here's what it says. If f and g are differentiable functions, then their product is differentiable, and the derivative of the product, f times g, is f times g prime plus g times f prime. So let me, I guess, like highlight some things just to like make it clear. So we have f, and then we have f prime, and then we have g prime and g. So it's, I actually say it a slightly different way. So what I do in my head is I say first, right? You have a first function and a second function, f and g, first and second. So it's first and then derivative of the second plus second, which is the same color as this, second, and then derivative of the first. First derivative of the second plus second derivative of the first. First derivative of the second plus second derivative of the first. First derivative of the second plus second derivative of the first. Say it with me. First derivative of the second plus second derivative of the first. You're probably not doing it, but you could be. First derivative of the second plus second derivative of the first. You don't want to enunciate too clearly when you're saying it. You lose kind of your cadence there. But anyway, that's how we can find the derivative of a product. So this is sort of mind-boggling. We're going to do a bunch of examples. So you could write it as first derivative of the second plus derivative of the first times the second. Where's your flow? There's like nothing about that that's poetic. It has no good cadence to it. So I always say first derivative of the second plus second derivative of the first. First derivative of the second plus second derivative of the first. Say it over and over again. Okay, so we're going to do a couple. Well, the first one we do, you're going to be able to do two different ways, so you can check it and see that it's true. There's definitely a proof of this. I have it on Turksvids. If you want to see it, go ahead. It's not super illuminating, so I don't think it's like helpful to really go through the proof. But if you're into that kind of thing, go check that out. Probably, I don't know, it's probably in the playlist for Notes 21 somewhere, I'm sure. And the person who like kind of came up with this was Leibniz, right? So there's Newton and Leibniz, calculus at exactly the same time, which is also insane. He was 29 when he came up with this, which is insanity to me. But that's amazing and good for him and good for all of us. So let's see if we can do it. All right. So find the derivative of each of the following. When you have some time, write your answer either as a single fraction or in factored form. It's important to be able to do that. So will we have time? I don't know. Let's see. Let's get this first one done. All right. So what are we dealing with here? We have a first function and we have a second function, right? And so to find the derivative, h prime of x, it's going to be first, so 4x cubed, times the derivative of the second, which is 7, plus second, which is 7x plus 2, times the derivative of the first, which is 12x squared. So you can see I'm using the sum and difference rule when I find the derivative of the second. I'm using the power rule when I find the derivative of the first, but it's first derivative of the second plus second derivative of the first. Let me highlight that for you. I'm going to just go through and like highlight in this color first because I have it available. And then here, first derivative of the second plus second derivative of the first. Okay, so then you want to be able to simplify these things. So let me do that. What should we do here? I'm just going to expand everything because I don't, well, no, actually I'm going to take out 4x, 12x. Oh, look at that. That's a mistake right there. Look at this guy. Ooh, I don't know how erasing works on highlighted stuff. Ooh, takes it all out. Right, so it's going to be 12x squared, right? Bring down the 3, subtract 1. Somebody forgot to subtract 1. Don't know who that was. Okay, so we're back. Okay, I'm going to take out 4x squared from everything. So we got 4x squared. So I'm going to be left with 7x for the first thing. And then I took out 4x squared from 12x squared. So that left me with 3. So there's going to be 3 times 7 is 21x's, and 3 times 2 is 6. Okay, so I get 4x squared, and then 28x plus 6. And then if you really, let me see how much space I have. I have a lot of space. Okay. If you really want to, you can keep going and take a 2 out. So I'm going to do that. So I'm going to get 8x squared and get 14x plus 3. Okay, so that's h prime of x, I think. Now, why would I have factored that? I factored that because, as we've seen, there's like something really important about the zeros of a derivative, right? Those are the places where the derivative can change from positive to negative, negative to positive, which means the function will change from increasing to decreasing, decreasing to increasing. When it does that, you can have a maximum or a minimum. So that's why we're doing this factoring. What I want to show, though, is I also, for this particular problem, it wouldn't have been that bad to expand. So if I had, let's change this up. Let's go with here. I could have rewritten h of x as 20, what are we getting? 28x to the 4th. Okay. And then plus 8x cubed. And then I could have just used the power rule on this, right? So if this is the case, then h prime of x would have been 4 times 28, great. That's 80 and 32, 112 x cubed plus 24x squared. Okay. If I factor this, okay, so the real question is, I can take 8x squared out of both of them. So 8x squared, or can I take 8x squared? Really, I can take 8x squared out if 8 times 14 is 112. So is 8 times 14 112? Yeah, it definitely is, right? Because that's how I got, how'd I get that to, I don't know, right? Oh, you know what? The easiest thing to do is I did 28 times 4, right? So here, let me show you over here. Follow me. I did 28 times 4 to get 112. 28 is 2 times 14, so it's really 2 times 14 times 4. And then 2 times 4 is 8, so 8 times 14. So yeah, definitely. Did I need to think about it that much? Probably not, but you know, that's how I think about these things sometimes, so I think it's useful to share that with you. But anyway, this will be 14x plus 3, and let's compare them. So we'll use this. So I got h prime is this, or h prime, same answer both ways, which I knew was going to happen because I know that the product rule works, but you probably are more skeptical at this point, as you kind of should be. I'm going to move this weird extra work over somewhere else because I'm probably going to need all the space for the next problem. Let's put her over there. Okay, so that's one down. All right, let's take a look at the next one. Am I going to have enough space for this? Almost certainly not, but we're going to go for it. All right, so we got a first and a second. So should I highlight them again? I guess so. First and then second, right? And the product rule is first derivative of the second plus second derivative of the first, first derivative of the second plus second derivative of the first, first derivative of the second plus second derivative of the first. Keep saying it over and over. Here we go. I'm going to say dy dx, because why not? All right, so dy dx, right? The first derivative of this weird function is going to be first, and then derivative of the second, so that's going to be 5/3 x. 5/3 minus 3/3 is 2/3, and then derivative of 1 is 0, and then plus second, x to the 5/3 plus 1. Derivative of the first is going to be -2, x to the -3. Okay, so what did we do? We did first derivative of the second plus second derivative of the first. I'm having trouble with my highlighting because I'm trying to do it efficiently, so I'm just using like the one color and then the other. Here we go. First derivative of the first. So first derivative of the second plus second derivative of the first. Color them up if you want. If not, totally fine. What the heck can we do here? All right, so in general, if someone just said find the derivative, but they didn't say simplify it, or if you had to evaluate this, the only value I can imagine plugging in here would be 1, maybe -1. But if you had to evaluate it, just go for it here. Don't bother simplifying. But if you have to simplify, let's see if we can do it. So dy dx equals, all right, so I'm going to get 5/3. So it's x to the -6/3 because that's x to the x to the -6/3 times x to the 2/3, x to the -4/3. This one I'm probably going to check on the calculator. Plus 20/3 x to the 2/3. So far, like, not terrible. Plus, all right, x to the -3rd is x to the -9/3 times x to the 5/3. -9/3 plus 5/3 is -4/3. So that's going to be, but it's also -2. So I'm actually, let me erase this and just go -2x to the negative, I think it was -4/3. It was -9/3 plus 5/3. Yeah, okay. So we get that, and then -2x to the -3. These are not easy to simplify. So like, I mean, I might mess this up. I hope that I don't, but I might. I'm seeing something that I don't like here. Oh no, yeah, okay. Well, I don't know, but I think it's okay so far. All right, what do I do now? Now I like to take everything with a negative exponent and drop it down into a denominator. So I'm going to make everything look like a fraction rather than the way that it currently looks. So it's going to be 5/3x to the 4/3 plus 20x to the 2/3 over 3 minus 2/x to the 4/3 minus 2/x cubed. Okay. What are we dealing with? All right, look at the denominators, right? We have a 3x to the 4/3. Okay, so that's like my base in my brain. I'm like 3x to the 4/3 might be the common denominator. So then the next thing just contributes to 3, that's fine. The next denominator is x to the 4/3, still good. Then the next one is x cubed. So x cubed is bigger than x to the 4/3. So that needs to become the x power in my denominator. So I'm going to go with 3 times x to the 3rd as my overall denominator. So to do that, I need to multiply. Am I gonna be able to squeeze this in? Like, probably not, but I'm gonna try. You know what? I'm gonna use some iPad magic here and space things out a little bit more. I think. How am I gonna do that? Okay, hold on. Okay, I'm struggling, but I feel like I maybe have this. I don't really know what I'm trying to do. Okay, space. I need some space. And maybe a little more space here. Okay, I think this will work. And then I'm gonna move the whole thing over a little bit. All right, thanks for bearing with me. So here we go. All right, I need here, because I need to get to 3x cubed. Oh, I lost a 3. Where did it even go? I must have deleted it at some point. You probably saw it happen. You're like, ooh, what movie magic happened there? All right, let's see. So, all right, this I need to multiply by x to the 5/3 over x to the 5/3 because x to the 4/3 plus x to the 5/3 is x cubed, x to the 9/3. Here, I'm also going to need that. So times x to the 5/3, x to the, oh no, I need a straight up x cubed there. I don't need x to the 5/3. I was looking at the numerator. Silly. X cubed. Here I need x to the 5/3. Had some like terms there that I probably should have combined. X to the 5/3. What's going on here? 5/3. And then here I need 3/3. But I also need a 3/3 here. Okay. Does it simplify? Let's see. This will give me, okay, 5x to the 5/3 over 3x cubed plus 20, so it's x to the 9/3, x to the 11/3. It's gonna be so sad when this is wrong. I'm gonna be sad. You're almost certainly also going to be sad. 6x to the 5/3 over 3x to the 9/3, which is that, minus 6/3x cubed. It's like not looking great, but I think it might be right. So equals, all right, we'll go with the highest power, 20x to the 11/3. Then I have minus 6x to the 5/3 plus 5, so minus x to the 5/3. And if you're thinking this will be the last problem we do in this video, you're absolutely right. Minus 6 all over 3x cubed. Whew, I don't know. All right, so let's go to the calculator and let's see. Obviously your calculator is a phenomenal resource on these problems. So if I want to find, so I just need the derivative. So derivative with respect to x of x to the -2 plus 4 times x to the 5/3. This is like, I'm gonna feel so depressed when this is wrong. 20x to the 11/3 minus x to the 5/3 minus 6 over 3x. Yes, we got it. All right, so that was right. Your calculator is a great resource on these because when you're doing these algebraically, you can get kind of lost. In terms of the calculus though, product rule, first derivative of the second plus second derivative of the first. Getting that step done was like nothing. Everything beyond that was sort of like a horror movie, but we did it. So, all right, I'm gonna stop this here. I'll come back in the next one, and we're gonna keep going and see how it goes. It's not gonna go poorly. I think we got this. So I will see you in the next video.